crystal of sodium chloride. We know sodium and chloride are not found by themselves, but in a unit crystal. And the chlorine is bigger than the sodium. Why is the chloride ion bigger than the sodium ion? Okay, more electrons put in there. One additional, okay, the ZF. Very good. So, the sodium much smaller again. It has, again, the electron configuration of the previous noble gas, neon. So this gives us the shape here. This is why sodium and chlorine fit so well together, form their crystalline structure. This is one type of solid. Let me show you some more really cool structures. This is why you can have, come on, clicker, there we go. These are atoms, ions, or molecules that lie in a highly regular arrangement, which we call a lattice. Typically have flat, well-defined surfaces called faces. So even though this here would be defined as a face, okay, even though it doesn't show, again, the three-dimensional nature of the material. So these are crystalline solids, one type of solid. Quartz, silicon dioxide can form either type of crystalline solid. You can have crystalline quartz that looks like this, and non-crystalline quartz which looks like this. This here is glass, and this here is a crystal which is not transparent to see through due to some of its different properties. Solids, crystalline solids can be molecular solids, which are composed of nonmetals. They have low melting points like ice. Ionic solids are composite units with cations and anions. These have high melting points, and they conduct electricity when dissolved in water. Atomic solids are included of metallic, network covalent, and non-bonding. So metallic bonds are just metals combined together. You can have a solution of this that's called an alloy. They conduct electricity very well. They're held together by metallic bonds, and they have various melting points, which tend to be higher than some of the others. Network covalent is one type of covalent bond we haven't mentioned much about. This is when atoms or smaller subunits connect together in a network. So instead of a water molecule here in ice having hydrogen bonds to other water molecules, this silicon dioxide has bonds, chemical bonds, between other silicon dioxides that connect together. This provides a very high melting point. The prime example of a network covalent solid is diamond. It has an extremely high melting point, and it is incredibly hard material. Network covalent tend to be solids. Molecular solids here are covalent molecules, and they tend to have much lower melting points than the network covalent. Non-bonding, this is the area referred to when there are no chemical bonds, but they still stick together. Here is solid xenon, a picture of solid xenon. They have incredibly low melting points. They're held together only by dispersion forces, so you're going to expect them to have low melting points for non-bonding. And this is when there is not a chemical bond, but only dispersion force holds it together, whatever the substance is. And this happens, solid xenon, liquid nitrogen, between the nitrogens, has a small amount of dispersion force happening there. A crystalline solid possesses rigid and long-range order. In a crystalline solid, atoms, molecules, or ions occupy predictable positions. So you can predict where they will be placed based on what ion it is. Yes?
Do substances with high melting points usually have high boiling points?
Usually. Depends on the forces that are keeping them together, though, a little bit. But most of these substances, like if you think of a metal, has a pretty high melting point. To get that metal to boil, even higher, much higher than that. So depends on what you're comparing it to, but yes, the high melting point means their boiling point is going to be above that somewhere. It tends to be much higher. So, for example, gaseous iron. Is it possible to have gaseous iron? Yes. Have we seen it? Most people on the earth? No. Sometimes you see liquid iron, for example, but you don't see gaseous iron very often. So you have to have a very high temperature. And then to get into a plasma, it has to be even higher. So the bond strength does determine the energy for that. Unit cell in a A solid is a basic repeating structural unit of a crystalline solid, so it repeats multiple times. It's called a unit cell. Here is a unit cell for a particular combination of atoms. Here's what a unit cell would look like in 3 dimension. A bunch of them attached together. This is a 9 by 9, or I'm sorry, 3 by 3 by 3 unit cell here. Looks like it. This is what is called the lattice point, which is the point here at the end of it, which tends to connect to other unit cells. At the lattice points are usually atoms, molecules, or ions. There's not empty space at the lattice point. Yes?
So for that unit cell, it would have 8 lattice points?
Correct.
So each one is a, okay.
And so lattice points, atoms, molecules, and ions. Again, there can be things in the middle of the unit cell as well. So here's a picture here of 2 different separate structures. This is copper chloride here and barium chloride here. This is copper +1 and barium 2+. Okay, you'll notice here that there's a lot of similarities in terms of the way they arrange, although in this case, chlorine on the top one is on the lattice points, and in this case, chlorine is in the middle, with barium being at the lattice points. So you can see, again, depending on the unit structure, you would have different lattice points for the 3-dimensional structure. And so these 2 cells have different properties, even though they have a similar, again, structure. There are 7 basic unit cells. This is the simple cubic one, tetragonal, orthorhombic, not rhombic, orthorhombic, sorry, rhombohedral, monoclinic, triclinic, and hexagonal. No, you do not need to memorize these. Ortho and tetra. So the thing about the tetragonic is it has a square at the bottom. Here this has a rhombus or even a rectangle, depending on how you look at it. So the square structure of the tetragonal, tetra means 4, that's why it has a square at the bottom. Ideally we could call it squaregonal, but square doesn't make a pass anything.
What about the monoclinic?
Monoclinic? That's a cool name, yeah.
What's the difference?
Why is it called a monoclinic?
Well, what's the
What's the
difference?
difference?
And orthorhombic, because they look the same.
This one is more rectangular. This one here, I believe it's trying to show that it has a different base. This is the different angles, alpha, beta, and gamma here. And so you've got the sides A, B, and C. So the difference is, if you want to get very technical, is the angles here are all 90 for the orthorhombic. Every angle is 90. Here, A and B are 90, but the gamma angle, this angle here, which doesn't look very easy to identify, is supposed to be not equal to 90. So whether this picture is accurate or not is a whole other story. But I see where there could be confusion for sure in the pictures. There are 3 types of cubic unit cells. You do have to be aware of the simple cubic here, the body-centered cubic. So simple cubic has nothing in the middle. Body-centered has something in the middle, and face-centered cubic here. And this here is unique because it has things in the faces. So it's hard to visualize which of these is in the face. I think that one is, that one might be, and I'm not sure which one of these is. That one looks like it's not in the middle of the face, but it's in there. Maybe it's on the bottom. That one, you think? Okay. Anyways. So, yeah, you've got this one here, and the face, the face, the face, the face. And technically there's nothing on the in the body. It's easier to see down here, I think. 1, 2, all right, done. You can have fun with this all day long, yeah? It's on Learning Point, and it's also on YouTube if you want to check it out. It's really cool. You can look at this for hours. You have that much time? What's up? So simple cubic, nothing in the middle. Body-centered has 1 in the middle. Face-centered has 1 in the middle of every face. It's at least the idea. visualization of this, you start tweaking it and you close your eyes twice and it disappears and moves. All right. Not an optical illusion. All right, now the arrangement. Here's the arrangement of identical spheres in a simple unit cell. And so they arrange themselves again on the lattice points. And so this forms at least an ideal square in terms of the shape. Number of atoms per unit cell. We've got 1 atom per unit cell is for the simple cubic, because you've got 8 atoms and you got 1/8 of them, so that means there's 1 complete atom per unit cell, because they're all on the lattice points. For the body centered, there would be 2, because there's 1 atom in the middle and then 1/8. What about the face-centered cubic? How many atoms per unit cell would be in the face-centered cubic? So the first one here, there's 8 atoms, and 1/8 of each atom is inside of the cube. So 1/8 of it, there's 8 of them, 8 times 1/8 equals 1.
Wait, what are you talking about though? What are you talking about?
The atoms per unit cell.
But there are 8 atoms.
But they're not all inside of the unit cell.
So you mean the amount of atoms that's inside?
Yes.
Oh, that makes so much sense.
So face-centered, we have an answer for this. 5. Any other answers? 4, 6, 5, 4, 6. Any others? 7. 92. Anyone? 92. 1? 4? How many? 4? All right, let's look and see. How did we do? Just a fun experiment to do. Make your brain tweak. 4 atoms per unit cell. There's the 8 on the outside, lattice points. 6 on each of the faces, half of those, and there's none in the middle. There's nothing in the middle. It's hard to visually see that in the picture, but none in the middle. That's why it equals 4. What's up? Because these here that are on the face, half of the atom is inside and half of the atom is outside the unit cell. So that's why it's happening. All right. Now, if you like doing those type of problems, again, in material science engineering, they do a lot of the cubic structures, and you can even look at different materials and how you arrange them, and it changes the structure of the material. Thank you. Anita. Oh no. All right, so getting back to an AP chemistry problem. Unfortunately, that last problem would not be on the AP test, but I don't think so. But maybe they can throw it at you if they really wanted to. But this one might be. When silver crystallizes, it forms face-centered cubic cells. The unit cell edge length is 409 picometers. It's asking us to calculate the density of silver. So density is mass over unit volume. So the first thing we would need to know is how many atoms are in that space. So face-centered, there's going to be 4 atoms per unit cell. So that information here can help us out. The volume is equal to the cell edge length, which is 409 picometers. Not sure why they put it in that good times. So 409 picometers, you cube that, you get 6.83 times 10 to the negative 23rd centimeters cubed. Okay? We're working with small numbers here. There are 4 atoms per unit cell in a face-centered cubic cell, so this is the mass is 4 Ag atoms. Multiply that by the molar mass of Ag. Divide that by the number of atoms in 1 mole. The atoms cancel. The moles cancel, leaving you with the grams of 4 atoms. So this is the grams of just 4 atoms. So it's going to be a really, really what number? A really small number.
Yeah, 4 atoms.
You gotta divide by Avogadro's number here. Otherwise, you're saying 4 moles of silver. So that's why we would get 7.17 times 10 to the negative 22nd grams. Then we just take the mass divided by the volume. It's a density problem. The mass is 7.17 times 10 to the negative 22nd grams. Volume is 6.83 times 10 to the negative 23rd centimeters cubed. And that gives us a density of 10.5 grams per centimeter cubed. That happens to be the density of silver. So this is a way of calculating the density of a substance if you know what type of cubic cell it forms. So the cool thing about that is if you know the cubic cell you make, you can calculate the density of the material, no matter what you put in it. You just need to know how many atoms of each you put in there. Yes?
Why is volume A like?
I don't know why this A is here, to be honest. It's the cell edge length, and that's what they use for the symbol for that.
I mean, that's what it is. Like, I'm looking at the actual. I saw unit cell, and I was like,
So why it's chosen to be this letter, that was something that kind of made me go, what? But that is for cells. Okay, for the cell here, you've got A, and A are all of they're all the same size. That's why they chose A.
oh, so it's just arbitrary.
Because it's all the same size in a unit cell. If it was a monoclinic or something, then you'd have A, B, and C. So that's why A was chosen. Sorry, I forgot the A. I think of it in terms of, length time, width time, height. You're fine. A happens to be the length and width and height. Now, the cool thing is, how do you find the arrangement for obtaining the X-ray diffraction pattern of a crystal? So how do you know what that crystal looks like? The cool thing was, what you can do is take an X-ray, put it through a slit here to make a beam of X-rays and shine it through the crystals. Okay? When that is shined through the crystals, the X-rays again can make an arrangement based on, again, how they travel through that crystal. This picture here can be interpreted as what is called X-ray diffraction or X-ray crystallography. And you can tell what type of crystal is formed. What happens is when the X-rays come in, they come in initially at a particular angle, theta, and if they make contact here with the first layer here, the collision, the X-rays get reflected. Okay, and it's at the same angle for each of these here. So what you're able to do is from this you can solve, okay, for the distance between the points, all of the angles, of course, okay, and the distances here to solve using a little bit of geometry, the distances between the atoms and where they're located. So what they use is they use the reflections to measure all of these components of a crystal, and that will tell you what type of crystal is formed. That's when you want to know the monoclinic and all those other ones when you're doing this type of data, because it'll tell you which one it fits, which pattern it would fit. This will tell you the distance between the reflected rays, and that is BC plus CD. And this is known as Bragg's law. Bragg, like, yeah, we're bragging because we came up with what? No. Bragg's law. Yeah. So you've got the d sine theta. You take 2 d sine theta equals n times the wavelength that you're working with. Whatever wavelength material and X-rays, you know the wavelength here. Okay. Let's look and see how we can apply Bragg's law to a sample problem. So X-rays have this wavelength, are diffracted at a crystal at an angle of 14.7 degrees. So we can measure the diffracted angle. We can assume that n equals 1. What is the distance in picometers between layers in the crystal? So using Bragg's law, this is the law we would use to determine the distance in picometers. You have to be given the n equals 1 or assume that n equals 1 and the angle that's measured. So that would be data you would collect in the experiment. Okay, the wavelength here is in nanometers, and you can convert that directly into picometers by multiplying by a million approximately. No, nanometers are bigger than the picometers. You need 4 picometers to equal 1 nanometer. So to find the distance, okay, the distance, you just solve this equation for D here. Yep. Lochin?
What is N?
N. N is 1 in this case.
No, like what is it in G? Is it like the
Look and see.
diffract something that has like the
I have to look at what N is again because it's not coming to me. All I remember is always assuming that N equals 1, which doesn't help at all because it always seems to equal 1. But the N would be a number referring to some sort of number, and I'd have to check and see what that is. That's all I remember solving Bragg's law problems my whole life. But that doesn't mean it can't be N equals 2. Yep. Don't cry for me, Archie. All right, that's yours. This is yours. You have 28 minutes. Pick a test, any test. You go back there. 28 minutes. I'll tell you to stop. All right. The N in Bragg's law. The N in Bragg's law, all I can find right now to remember is not enough. It just says N is an integer. So about all it says is like Okay, it doesn't help me conceptually, but the good thing about n, since it's always an integer, it will always be provided to you. So it will be provided to you. You don't have to assume that it equals 1 in a problem like this. So if you are provided with this information, you can use the equation, Bragg's law, to solve for the picometers. The key things that people usually mess up on are the conversion between nano and picometers. Okay, or typing this into their calculator wrong, which hopefully doesn't happen. Yeah.
Okay, just to clarify, picometers is -12, right? Yeah, I think according to that side, it's
Nano.
nano is -9.
It would be. It's more than that. Nano to pico. Just say what it is. Nano's 10 to the negative 9th? I can't remember picometers. Yeah.
Oh, I think I know what N is.
You do? Yeah?
Isn't it like water and equals 1? I remember in physics you guys kind of wasn't it the difference between like air density and water?
Air and water?
Yeah, like it's different.
Oh yeah, N. N is the the density, the material you're using.
Waters is I remember N equals 1 in water, and then it's different for everything else.
Yeah, that's when you're shining light through different mediums. I remember that N too. I'm not sure if they're the same, but they probably are because it's electromagnetic radiation. Cool. All right, yeah, nano to pico still doesn't look right to me. Oh yeah. Yeah, pico is the 12th and nano is the 9th. All right, the next area we're looking at is molecular solids. The lattice points are occupied by molecules that are held together by intermolecular forces. So this is like ice, water, for example. They tend to be very soft and have low melting points. They're poor conductors of heat and electricity. Carbon dioxide, water, benzene, sugar are all examples of molecular solids. They do have some different properties. For example, water and benzene, this is liquid water and solid water, and liquid benzene and solid benzene. Okay, water is the one exception to most materials. Water floats, the solid floats. Of most other materials, the solid sinks to the bottom because of its density. The next type of substance, molecular solids. There are strong covalent forces within the molecules. There are weak covalent forces between the molecules. So sulfur S8 and phosphorus P4 are examples of molecular solids. Ionic solids are lattice points occupied by cations and anions, like NaCl. They're held together by electrostatic attraction, the positive and negative charges. They are very hard, brittle, and they have a very high melting point. Because in order to melt them, you have to, again, separate all of those bonds, or as many as possible, to get it into the liquid phase. They're very poor conductors of heat and electricity. Yep.
So, in the earlier slide, we have confusion about soft.
Soft. Okay. So.
Is that like
No, it's like the material itself is
Physically soft.
physically soft, or even sometimes compressible without cracking. There's another characteristics like sugar. Yeah. They tend not to be very hard on the Mohs hardness scale, diamond being the highest. Ionic solids. They don't conduct heat or electricity very well at all, very poor. Cesium chloride here. What type of cube is this? Which center? Body centered cubic here. A little harder to tell. Yeah, it looks like it's got some. And here's calcium fluoride. Gets a little more complex as you see different combinations. Here are atomic solids. This is when atoms occupy the lattice points. They're held together by London dispersion forces. They are soft and they have a very, very low melting point. They're very poor conductors of heat and electricity. Noble gases tend to be atomic solids. Again, you have to reach a very low temperature in order for them to become solid. Metallic solids. The lattice points are occupied by metal atoms. They're held together by metal bonds, soft to hard, low to high melting point. So some are softer on the left side of the periodic table, harder on the right side of the periodic table. They're good conductors of heat and electricity because those electrons flow freely. Here's a metallic crystal. The nucleus and the inner shell electrons are there as positive. The mobile sea of electrons is outside of that nucleus. And that's the electron sea model. In network covalent solids, a molecule looks like this. A network looks like this, where it actually has chemical bonds between the subunits. So this here is silicon and oxygen with a chemical bond between the silicon and the oxygens to make a network. And this network usually goes in multiple directions, and this provides for a very hard material. The lattice points are occupied by atoms. They're held together by covalent bonds, many covalent bonds. They have a very high melting point and are very hard. They are poor conductors of heat and electricity. They still don't conduct because they're all nonmetals. You have to have a metal. You have to have a metal in the substance for it to conduct. And ionic do not conduct unless they're dissolved in water. So when you add nonmetals only, they won't conduct. SiO2, diamond, and graphite are all good examples of network covalent solids. Okay. This is sand, this is diamond, and graphite, which sometimes is used in artists' pencils. Diamond versus graphite. They're both the same type of bonding. However, here's what looks different about them. The diamond has a three-dimensional structure in which the carbons are attached in tetrahedral shapes. The graphite forms hexagonal planar shapes. So in the graphite, the hexagonal planes can slide past one another, making the graphite a much different material and not as hard in terms of its structure. But because it can slide, it still provides protection. The carbon atoms here, okay, diamond's properties, much different than graphite's properties, and can be much different in terms of the arrangement of the atoms. Some of the universal properties of graphite is there's weak bonding between the layers. And so the layers can slide within and next to each other. They form these rings here. And you can notice here, what does this double arrow mean between these two structures? Could be equilibrium, but what is it actually called? Resonance. So it's resonance, okay? It's an average of the two of those. So the electrons are all here in pi bonds being shared equally around in these rings. So they flow pretty easily in graphite between the ring structures. The last type of solid is a network atomic solid. Some covalently bonded substances do not form discrete molecules. So diamond here does not form discrete molecules. It's the hardest mineral, it's an insulator, it's transparent, and it's the best abrasive. So if you really need to clean something, use a diamond. Graphite, though, is the softest mineral. Good electrical conductor, and it's a great lubricant. And it's great in pencils if you can afford them. It slides very easily, so the graphite can slip very easily. So it is very soft in its structure. Yeah?
I thought you said graphite was network covalent.
It's called network covalent, but it's only one type of atom in it. So they also call it a network atomic solid because there's only one atom in it. It's only carbon.
I thought to be a good electrical conductor, you said it has to have a metal.
Graphite's one of those fabulous exceptions to the rule. Yeah. Most of the time it has to have a metal in it, but carbon always defies us because of those pi bonds. So here is a sample AP test question based on solids. Okay, based on solids, this is 1977 letter D. Let me see, I think I put it in your lab manual, so you don't have to copy it down. So. All right, so this here is, yeah, you probably don't have it in your lab manual right now. That stinks. Didn't work out the way I wanted. Nemo. Oh well. All right, so what we're going to do, we're going to take a 3-minute break. You can think about this problem here. It is on the back of your lab, so we may not be able to do it today or tomorrow. Couple things you need to know, announcements for you. First of all, one thing about the labs. I know some of you were completing or in the process of completing Lab 12, and there was a scheduled lab quiz for next week. That has been postponed. So after the next, at the end of the quarter. Next quarter, pardon me. Quarter 3. No! The reason is I still have your Lab 12s, and it covers Lab 12, and I wanted everybody to have that back by the time they did that. Plus, we would have to grade them and get them all done, and not enough time to do everything. Plus, I want you to focus on the review for the final, so we can do better on the final. If it makes you happy, cool. If not, no problem. All right. For reaction quiz 5, that's complexation reactions. That's on Friday. I think these dates are wrong. I'm supposed to cover this earlier. So let me show you what that would look like for complexation reactions. so we're gonna, in about 4 minutes, we're gonna go through these problems here. What I'd like you to do is try to answer these questions in your group. You can work on it individually or with the help of other people. All right, ladies and gentlemen, let's look at, these are examples of complexation reactions. So in this one here, we've got excess concentrated aqueous ammonia added to a solution of iron 3 bromide. So what are the reactants, first of all, for this one? NH4, NH3, okay, NH3, added to Fe, and what else? You don't have to worry about the other stuff? Think it cancels?
Wait, so you don't need a charge for
Ammonia doesn't have a charge, yeah. All right. Now, if we put these two together here, then what could be produced here?
Iron, ammonia.
You got iron. How many ammonias do you want? 6 of them? You want 6 of those? You want a bracket? You want a 3 minus here? 3 plus? Correct, iron 3 hexamine. Now, on this quiz on Friday, you do not have to know the nomenclature. So we're only going one way right now. But the answer here, once you have that written, you would have your balanced equation. You'd have to go back and balance the ammonias, obviously. And you just have to keep track of the charge when you're making a complexation. Making a complex. Ammonium is NH4 plus 1, it's not a ligand. That's correct. Ligands are no charge, tend to be no charge, or tend to be negative most of the time. So Lochan, if you think about the ligands are attaching to a metal, so they tend to be no charge or negative in general. Yeah. Why doesn't it combine with this? The bromine does not, because this solution here is soluble, so the bromide stays separate from that, and there's not enough attractive force to get them together. So. This here is called a coordination complex here. That's this. So the bromine would not be involved with that particular compound. So it's usually the ion or the ligand, not the ion, but the ligand. So if you had bromide on one side and iron, something else on the other side, you could have bromine come as a ligand, bromide possibly. I don't know how likely bromide is as a ligand. So only time you got hydroxide separate would be alkali metals usually, like lithium, sodium, potassium, magnesium, and calcium. Calcium is on the issue part. And once you get on any other transition, there might be an exception if I'm thinking about it, but I can't think of any. All right, complexation. You just need to remember the rule of thumb. What's the rule of thumb? Except for aluminum. Double the charge except for aluminum. All right. At this time, we're going to talk about the lab we did yesterday and some of the properties you saw. These are referred to as colligative properties. This is states of matter, part 3. The cool thing about colligative properties is that solutions, there are many different solutions. Most people think of solutions as being a solid dissolved into a liquid. But you can have gas and gas, gas and liquid, gas and solid. You can have liquid and liquid. This is when two liquids are hold on one second. Let me get our friend out of the back. All right. So our liquids and liquids, that's like ethanol and water. They're infinitely soluble in one another. Immiscible refers to two liquids that are not soluble in one another, and if mixed, separate into two layers. Water, pretty easy there. But come on, liquid and solid and liquid. Solid and solid is a solution. That's called an alloy. So it sounds kind of crazy having to be a solution, but that's an alloy. You would have to heat the alloy up to its melting point, and then you would have liquid and you'd have your solid and solid would have the liquid and liquid, but it's still the same substance. But you've got some unique things here. This is how solutions are defined. Some key terms. Solution. A definition of solution is important. Okay? A general term for a solute dissolved in a solvent. Homogeneous mixture of two or more components at which the particles intermingle at the molecular level. So it has to be homogeneous, and that is defined as a solution. Solution and homogeneous have to be synonymous. The solvent is the component of solution that is in the greatest quantity, and the solute is the component that is in the lesser quantity. Like dissolves like, we've talked about this a little bit before. Two substances with similar intermolecular forces are likely to be soluble in each other. Nonpolar are soluble in nonpolar. Carbon tetrachloride in benzene. Polar molecules are soluble in polar solvents. Okay? Ethanol in water, for example. Ionic compounds are more soluble in polar solvents, like water. So salt in water or ammonia, both are polar solvents. Solvation is when we have, again, the positive cation here in the middle, surrounded by the negative polarity side of the water molecules. And this here, sorry. This is the interaction of the solute with the solvent, which leads to stabilization of the solute species in the solution. Hydration is when the solvation occurs where water is the solvent. So most of the time this is hydration, but you could also call it solvation if it was not water. Solution equilibrium. Here we've got NaCl placed in water. You've got a big chunk here. What's going to be taken off first are the outside molecules, they're going to be dissolved, and there's also going to be ions depositing on the sodium chloride. It starts out with just solid sodium chloride. The solid sodium chloride breaks up into sodium and chloride, and then when the rate of dissolution and deposition equal one another, this is where you have it dissolving and reforming constantly. This here would be if you still had a solid amount of solid at the bottom. Okay, and this happens especially with sugar. Sugar in tea, if you put like the whole can of sugar in your tea or your coffee, because you hate coffee, you pour all the sugar in, and you get to the bottom, the coffee tastes better and better. You get to the bottom, and then you look at the bottom, and you got a solid sugar at the bottom, and like a little bit brown. That's about it. Okay. Some people like to do that with their coffee. Starbucks has made millions of dollars off putting sugar into coffee, and people like it. But the sugar is similar. It's not the same, but it's similar. Okay, sugar has different attraction within itself, so it doesn't tend to break apart the same as NaCl. But this here is a equilibrium process where it's going forward and reverse. Here, there's a solution of KF. In the KF solution, you see the water molecules completely surrounding the cations and the anions. Are the same sides surrounding the positive and the negative ions? Nope, opposite sides of the same molecule though. The molecule just flips around, okay? So that's one way of thinking about it here. Sometimes people imagine that this here is the face of the water molecule, the negative oxygen, okay? And this here is the backside of the water molecule. And here they're all facing out away from the negative, and here they're facing in towards the positive. So if something positive is happening, all the water molecules are looking at it. If something negative is happening, they all show their backside. Three types of interactions in the solution process. First is solvent-solvent interaction, solute-solute interaction, and solute-solvent interaction. This is called hydration. The molecular view of the formation of a solution. The first step is the solvent. Okay, needs a certain amount of enthalpy to separate. The second step is the solute needs a certain amount of enthalpy to separate. So the solvent is attached to itself, attracted to itself like water sticks. The solute is attracted to itself, such as a sodium chloride a particle or crystal. And so step one is the solvent breaks apart. Step two is the solute breaks apart. And then step three is when they come together, the energy for that step. So you can have three enthalpies here for this entire process. So this is a way of breaking up this process of making a solution into three steps. And of course, for the entire thing, it's the sum of all the steps. Whose law is this? Hess's law again, okay, or a summation of some sort. So here's the steps. Solvent-solvent, solute-solute, which tend to be positive-positive, and then making this solution here. In this particular case, the solvent-solute has a negative delta H, and so the delta H for the entire process is negative for this solution. Now, if it's got a negative delta H, is it going to be exothermic or endothermic? Exothermic. So this is an exothermic process for dissolving a certain property of material. This is an endothermic process for a different material. It has to be a different material. Can't be the same material doing both. Yeah.
Wouldn't solvent-solute interaction be positive? Because solvent-solute is when you're combining them together and like forming things. Usually you said it releases energy. Oh, so it's negative. Never mind.
You got it. Yep, exactly. You got it. Yeah, sometimes it's really beneficial to talk out, hey, what's really going on? Anytime you deal with energy, you just got to stop and think about it a second before you write your answer. At least that's what I do. Think about what's happening at the molecular level. Okay? So in this case here, breaking apart, forming, breaking apart, forming. The only reason this one is net positive is the energy for forming doesn't release enough energy. It takes more energy to break it apart than to form it. And so this is why you have this positive delta H. This is when you have a solution that gets a lower temperature. Now, the delta H can be either positive or negative. It usually isn't zero, just as a heads up. It's usually positive or negative. It's very difficult to get it back to the same exact position with no energy change. So you've got the enthalpy to break the crystals apart, the enthalpy of disrupting the solvent structure, which is the solvent-solvent, and the enthalpy for hydrating the solution. So this is a really advanced way of putting tons of words up here that means break, form. That's it. I mean, to be honest, look at all these words. Enthalpy to break the crystal, break apart. Enthalpy of disrupting the, break apart. The enthalpy change for hydrating the solution, come together. Enthalpy is just the delta H there. Now, concentration units. The concentration of a solution is the amount of solute present in the given quantity of solvent or solution. So, one way of measuring concentration is percent by mass. To do this, you just take the mass of the solute and divide it by the total mass. So percent is the amount per 100. So percent is just solute divided by the whole thing. That's it. Times 100, of course, because you got percent. Yeah. This is an easier way of including this. The next type is mole fraction. A mole fraction is the moles of A divided by the sum of all the moles of all the components. So it's the part of A over the whole in moles, because it's called the mole fraction. Percent by mass, it's mass, because it's percent by mass. Molarity, most common chemistry unit, that's moles of solute per liters of solution. This is the most common, but not always the most beneficial unit. Molarity is commonly used because moles is the amount, liters is the volume, amount per liter is a measurement of concentration. Easiest way to do it. But molality, this is our new friend. Molality is the moles of the solute divided by the mass of the solvent in kilograms. Yeah, we did, but we have to reintroduce it because it's our new friend. Now, I do have bad news. In 2 years, the students won't have to learn about molality. So,
Why 2 and not 1?
I don't know. It's just
Why not now?
why not now? They have a new chemistry curriculum coming out in 2 years.
Oh, really? Does it cut down a lot of stuff? Oh.
It's just mixing things up. They decided to take molality out of it and add a bunch of other things. No, there's some pluses and minuses. All right, now, the reason we use molality is because of our lab experiment. We have to use molality for our lab experiment, so that's why it's an important unit for us. Molarity is used all the time in chemistry, so that's why it's the most important concentration unit. Molality, I would say, is a close second. In America, percent by mass is, or percent by volume is usually how you find a solution. So when it says 70% isopropyl alcohol, that's percent by volume. So it's not percent by mass, but percent by mass is pretty easy to calculate if you know the others. This is the important difference between molarity and molality. Liters of solution, and that's mass of solvent in kilograms. So that's a big difference. It's still moles and moles, but that's the big difference there is solvent, not solution. And it's in kilograms, not liters. So here's an example problem here. You've got 1.36 grams of magnesium chloride are dissolved in 47.46 grams of water to give a solution with a final volume of exactly 50.00 milliliters. It's asking you to calculate the concentration of the solution in mass percent, parts per million, mole fraction, molarity, and molality. A lot of equations. somebody asked if we could have the answers really quickly because it's just too much work. It's not really too much work. It's just a matter of remembering how you calculate each of them. But this is how mass percent, the solute over the solution times 100. Part per million is the mass of the solute over the mass of the solution. So it's kind of the same here, but then you have to multiply it by 10 to the 6. That's all you got to do. So parts per million is commonly used on the California Standards test. So just be, you won't need that till much later, and it'd be a super easy test anyways. But yes. Yes, it should be online. If it's not, it will be online, but I believe it is. Mole fraction. You got to convert grams to moles, and then grams to moles for water and magnesium chloride. So this requires a lot of mole conversions. So it just takes a little bit longer to do. Yes, sir.
How can parts per million be mass to mass? Would it be like number of particles?
Seems like it would, but parts per million, parts per billion are all mass to mass, and then times 10 to the whatever power. Yeah, it's kind of weird the way it's worded. It's really a percent, and then you multiply it by a different factor. Percent is parts per 100, which is weird. Yeah. The mass per mass of solution, and depending on what you have. So, here's molarity and molality, which is the big difference one we'll use on our lab. So tomorrow we'll talk about how to use molarity and molality. Thank you.